Hi everyone, I'm Krishna Subramani from the Indian Institute of Technology, Bombay, India, and I will be presenting our work on variational parametric models for audio synthesis or VaPar Synth. So what comes to your mind when you hear audio synthesis? So is it like one of these early Moog modular synthesizers which had patches you could connect to and synthesize really interesting audio? So yes, indeed. Analog synths like the Moog used voltage-controlled oscillators, filters, amplifiers, etc. to generate and envelope generators to shape waveforms. However, with the advent of data-driven statistical modeling and abundant computing power, why not harness the tools of deep learning for audio synthesis? So this is like our idea of a generative synth with controls as timbre, pitch, and loudness. So timbre is that aspect of a sound which makes a violin A4 sound different from a flute A4, both played at the same loudness. It could stem due to temporal or spectral characteristic differences in the sounds. Pitch is essentially the fundamental frequency of the note being played, and loudness is the intensity or the energy with which the note is being played. With these parameters in control, we can generate, or we would like to generate really interesting sounds with our generative synth. Saroff and Casey were the first to perform frame-wise reconstruction of short-time magnitude spectra with autoencoders. They extracted the audio from the sustained portion of the sound and performed frame-wise autoencoding. Roche tried out different autoencoder architectures and also analyzed this lower dimensional representation of the audio or the audio latent space. Essling regularized this latent space for better control over the timbre of synthesized instruments. Some issues with these previous methods were that the frame-wise analysis synthesis-based method does not take into account the temporality of the audio, and there could be phase estimation issues when trying to invert a spectrogram. So Engel, inspired by WaveNet's autoregressive modeling capacities for speech, extended it to musical instrument synthesis in the waveform domain with NSynth. Weiss also proposed generating audio samples with RNNs, but he also proposed to condition the waveform generation on additional parameters such as pitch, loudness, and the instrument class for better control. DeForze also proposed frame-by-frame waveform generation with LSTMs. One commonality with all of these methods was that they chose to work with audio in its raw form, either in the time domain or the spectral domain. So why move on to parametric modeling? So consider the task of synthesis of a given instrument sound with flexible control over the pitch. As is known, pitch shifting without timbre modification requires the use of a source filter model with the filter or the spectral envelope being kept constant. The advantage of a powerful parametric representation, either over the waveform or the spectrogram, is the potential to achieve high quality synthesis with less training data and the ability to generalize better, provided of course that the parametric representation we use indeed works with the audio. Keeping these in mind, Blau and Bonada used a vocoder representation to train a generative model for speech synthesis. Engel also recently in differentiable digital signal processing proposed the control of a parametric model based on a deterministic autoencoder. The dataset we use is the Good Sounds dataset by Romani Picasse et al., which is individual note and scale recordings for different instruments. So we work with the violin recorded in the mezzo forte or medium loudness and the fourth octave, which is the mid-level pitch range. So why violin, if one asks, it is very popular in Indian classical music, especially in South Indian Carnatic music, where it is used as an accompaniment. And also because of its human voice-like timbre and its ability to produce a continuous pitch. To provide some further motivation to use a parametric method, here is an experimental setup of a non-parametric reconstruction where while training a model, we both include and exclude MIDI 63, but train with the 3 nearest neighbors on either side. And we reconstruct the MIDI63 and see how well the network performs. So the reconstruction is essentially extracting frames from the sustained portion of a MIDI63 note and autoencoding it through an autoencoder, and then inverting the obtained spectrogram with the Griffin-Lim algorithm. So here is an input MIDI63 note. And here is the reconstruction when the network has been trained with MIDI63. As you would expect, the autoencoder has information on what a MIDI63 waveform, spectrum looks like, so it is able to reconstruct it reasonably well. However, when you try to reconstruct a MIDI63 on a network which has not seen it before, the network has no idea what to do, so it completely destroys the timbre, as you could possibly see from the spectrogram as well. So the parametric model we use builds upon the harmonic plus residual model by Serra. The harmonic plus residual model essentially finds out the harmonic locations and the peaks in the magnitude spectrogram. The second step is, with these harmonic peaks, we find out the spectral envelope using the true amplitude envelope algorithm, originally by Imai. What the true amplitude envelope algorithm does is gives us a smooth function which allows us to sample the harmonic amplitudes from. This amplitude envelope is parametrized by the Kepstrel, is represented by the Kepstrel coefficients. And the smoothness depends on the number of coefficients, which is chosen according to this expression here. So the true amplitude envelope algorithm has no open source Python implementation. We have implemented it following the procedure highlighted in these papers. So for an audio like this, this is the parametric reconstruction following the procedure highlighted, which is reasonably good. However, we have to keep in mind that we have only reconstructed the harmonic portion and not the residual. So these are the examples of a few spectral envelopes for different pitches across the octave. So as you can clearly see, there is considerable variation across pitch. This could be because of the dependence of envelope on pitch, which in turn is because of the non-independence of the source and filter for musical instruments, unlike for speech. Or the dependence could also be because of variations introduced due to the TAE algorithm itself. However, the advantage that this envelope gives us is that it gives us a smooth function which we can use to estimate the harmonic amplitudes. So just a brief touch up on generative models. Autoencoders find out an optimal, in terms of the mean squared error, lower dimensional representation of the input. Variational autoencoders enforce a prior on this lower dimensional representation. And conditional variational autoencoders enforce a conditional prior by additionally conditioning the input on an external variable. So why use a variational model over an autoencoder? Is because a variational model gives us a continuous latent space from which we can sample points and thus synthesize the corresponding audio. And why additionally condition? Conditioning on pitch allows the network to capture the dependencies between the timbre and the pitch, which in turn allows for more accurate envelope generation and additional and more refined pitch control. This is especially useful in the context of Indian music, where pitch is not necessarily discrete but continuous. So we would want to synthesize audio for the continuous pitch contour, given these discrete pitch as training data. So this is the network architecture we use. So the input to our conditional variational autoencoder is the Kepstrel coefficients, and the conditional parameter is the pitch for each frame. And because the input is the Kepstrel coefficients, the mean squared error represents the perceptually relevant distance in terms of the squared error between the input and the reconstructed log magnitude spectral envelopes. The main hyperparameters of our network are beta, which represents the trade-off between the reconstruction and prior enforcement, and the dimensionality of the latent space, which controls the network's reconstruction ability. From the plot on the left, we can see that as we increase beta, it places more emphasis on the prior enforcement than the MSE, and thus the mean squared error increases. So we choose a value of beta to be 0.1, as we also would like to sample points from the prior. With this value of beta, from the graph on the right, we can see that the MSE reduces drastically till dimensionality 32, and then is almost the same. So hence, we chose to work with a latent space of dimensionality 32. We performed the following two kinds of experiments to demonstrate our network's capabilities. Reconstruction, which is omitting pitch instances during training and seeing how well the model reconstructs those target pitches that have been omitted. And generation, to see how well our model synthesizes note instances with new unseen pitches. So in the reconstruction experiments, we provide two training contexts. The first is training excluding MIDI 63 and training it with the nearest neighbors around it, and reconstructing it similar to the non-parametric reconstruction method we followed earlier. So with an input MIDI 63 node, this is the network's reconstruction, which is quite good considering the network has not been trained on MIDI 63. And here is the previous non-parametric spectral reconstruction, in which case, if you remember, the timbre was completely destroyed. The next training context is by training on the octave endpoints. So we train on MIDI 60 and 71 and skip all the intermediate pitches, and we reconstruct all of them. The plot to the left essentially describes the MSE for all of these reconstructed pitches between 60 and 71. And we can see that the MSE for the CVAE is consistently lower than that for the autoencoder. This reinforces our belief that the conditioning captures the pitch dependency of the spectral envelope more accurately. So here is an example of a MIDI 65 note, which the network has clearly never seen before, having only been trained on 60 and 71. And the network reconstruction, which is not bad at all, given that the network can only work with 60 and 71 to interpolate and find out what it feels is the most optimum reconstruction. For generation, we would like to generate or synthesize unseen or untrained pitches. So this is the setup for generation, where we sample points from the latent space and provide the pitch as a conditional input to the decoder. Since we want to synthesize an audio, we would like to sample multiple points in the latent space. So to do that, we perform a random walk with a small step size to coherently sample the envelopes. And we sample the harmonic amplitudes from this envelope and perform a sinusoidal reconstruction to obtain the audio. So this network has been trained on the entire octave with the MIDI 65 skip, and we use the network to generate MIDI 65 and see how well it does it. So this is the network generated MIDI 65 note. And this is a MIDI 65 note from the dataset. So the harmonic part is reconstructed reasonably, but as we have not modeled the residual, it still sounds a bit synthetic. So for a more violin-like audio, we introduce a bit of vibrato into the synthesized note. So putting it all together, we have explored autoencoder frameworks in generative models for audio synthesis of instrumental tones. And we feel a parametric representation decouples the timbre and the pitch, and the network further models the interdependencies. Pitch conditioning additionally allows us to generate spectral envelopes for that specific pitch, which further allows us to vary the pitch contour continuously and obtain coherent envelopes and audio. But a few limitations of our models are the lack of residual modeling, which you could hear from the previous note, clearly affected the perception of the generated note. We have also not taken into account dynamics or loudness changes, which might affect the timbre as well. And because of the frame-wise model, we have not taken into account the temporality of audio. So the concluding thoughts are, we would like to build a system that can synthesize melodic elements from Carnatic music. Which clearly is a very challenging task. And to the best of our knowledge, we have not come across work using parametric models, and one which exploits the conditioning function of the CVAE. All of our code and audio examples are available on our GitHub repository. So thank you. Here are the references, and here are the descriptions of the audio files played. Thank you once again, and have a good day ahead.